Hi, I'm Mahesh Paulini Subramania. I am, oh, no title. Cool. I basically head up software at a company called Ubiquity Networks. Anybody here heard of us? Ubiquity? 1, 2, 3, 4. Okay, Ubiquity Networks is the largest network hardware provider that all but 4 of you have never heard of. It is. We basically build hardware that you use to hook up any two places that you can't pull a cable in between. So anything from like Wi-Fi hotspots for rooms to microwave cannons that you can use to do gigabit links between any place that you got line of sight connections between, long haul Wi-Fi. Remember those Pringle cans that you could use to do whatever? We productized that. We sold a couple million of those. I mean, it's amazing. So we're this big, huge, multinational company, whatever, which makes Pringles cans. It's great. So on a serious note, I head up software for the company, and today what I'm going to start with is break the first rule, which is I'm going to tell you what I'm not going to be talking about. You're not supposed to do that, by the way, in case you didn't notice. So I'm not actually going to be talking about Erlang the syntax or Erlang the specifics of the language, because quite frankly, you can pick that up anywhere. You can get it in a book, and if you really want to know more about it, Robert Verding, who's one of the creators of Erlang, is teaching a course over the next 3 days just down the road, and heck, I couldn't recommend it higher. He's brilliant, and it's a great course. That said, what I'm going to be going over is kind of the philosophy behind Erlang. What's the origin story? Why would you, A, write stuff in Erlang, and B, think in Erlang, which is probably much more important. What's essentially happened now is, after years and years and years of Erlanging, I do everything in Erlang. And when I say everything in Erlang, by the way, I'm not just talking about writing applications. We architect our systems kind of in an Erlang style. Hell, we architect our organizations in an Erlang style. My development teams are set up as if they're Erlang applications. This will make sense by the end of the talk. Trust me on this. Yeah. So, Erlang. So the real thing is, at the end of the day, shit happens. And you really have no control over this. Have you heard of Nicholas Taleb, the Black Swan? Yeah, okay. That's going to happen. You got no choice about that. What you want to try and do is prevent yourself from shooting yourself in the foot before the Black Swan shows up. At least control the things that you have some control over. And we're going to get into some of that. But let me start with a little story, kind of give you a bit of context around all of this. So, it didn't take very long for my thing to stop working. There we go. So this is a story. This begins about 3 years ago. I was about to head out on vacation. And that, by the way, is not the Taj Mahal. That is something called Bibi Ka Maqbara, which is somewhere in the middle of India. It is the guy's grandson. He built this on the cheap. It's mostly like concrete and bad stone and stuff. It's still pretty spectacular, but it's not the Taj Mahal. We were going there to see this place and these ancient things in India, whatever. I was in New York about just across the river on that side. So this is where we're going to end up. To be really precise, this is the day before we ended up out there. So here's what happens. I got a flight on British Airways at 8 p.m. that night. London, Bangalore. Life is going to be great. 2 weeks off the grid, party. Little tiny failure in one of our servers. So a bit of context here. I used to run a phone company. I'd started a phone company in 1999. It had built up to this big, huge honking thing. We were scattered across end data centers and hosting providers and whatever, and it was this great, huge thing. It was great. But by the way, if you ever want to run a phone company, don't. But for those of us who did, it was fun, good money, blah, blah, blah. One server, one little tiny server in a rack somewhere crashed. So what do? We had architected our systems beautifully. A server, one of the processes crashes, just click the button, hit the start button, boom, it bounces the server, everything's good, it comes back up, everything's okay, except as it turned out, when I say boom, I mean everything went down. When I say everything went down, I mean we went down worldwide. It wasn't just the East Coast is down or US is down. I mean, we were down completely. So we kind of did a little bit of postmortem about the thing, tried to figure out exactly what happened, why did one little tiny server being rebooted cause this kind of cascade effect that went everywhere. And it turned out there were a bunch of little tiny things that all kind of interconnected and reacted together. So somebody makes a phone call, can't get through because it says system's down, or that one particular node that their call would have been on is down. So what do you do when you don't get through? You call again, and you call again, and you call again, till you get through. I mean, that's what everybody does. So effectively what is happening is, because that one node was down, the call volume spiked on that node by like a factor of 3 or 4. Makes sense. We had this little fail-safe in our system. When a node goes down, we just route the calls to voicemail. Yeah, you know what, fine, it's smart, it's a smart thing to do. So do that. Didn't think, little tiny detail, voicemails get transcribed. Voicemail transcription sucks up CPU. So all of a sudden, CPU starts spiking on a couple of other nodes, and those nodes start crapping out. Eventually, so you got not just the main node, the backup nodes are going down because the CPU is spiking. Eventually, the caches start timing out, and there are caches everywhere. So we start loading stuff from disk. You can see where that goes. So, that was just a complete disaster happening. So at this point, East Coast goes down, boom. Once the East Coast went down, people are just flooding the Facebooks and the Twitters and the what have you, saying, you guys suck, do whatever, sending us emails. So basically, our HTTP and our web servers are being hit off the charts. Script kiddies are at work. You get the point. Everything goes down. And, I mean, it really was like a complete, full-on, hardcore down. So the obvious question is, the really obvious question that comes to mind here, didn't you guys test stuff? Right? I mean, that's what you do. You should have known, you should have tested. Did you do any live testing? Did you bounce servers? Did you whatever? And the thing is, yes, we did. We absolutely did. Iowa, the 1,000-year flood. Katrina, the 100-year storm. It's like, when you stop, oh, hey, you know what? We're set up. If an asteroid hits Equinix East, we're still good. We're in Equinix West. No, fine. Asteroid hits Equinix East, and another asteroid hits Equinix West. What do you do then? Well, no, then we go to our backup center in Fukushima. Yeah, fine. So the bottom line behind all of this is black swans, and this is just the point I'm trying to get at behind this. This is the background here. Shit is going to happen. The black swan is going to kill you. The thing that hit us was that weird, bizarre 1,000-year flood that you really can't expect. It is going to happen. And quite frankly, there's an entire other talk about how do you survive and how do you react appropriately to black swans. And what do you do about black swans? And how do you minimize black swans? This isn't that talk. The whole point behind this is, you're hosed anyhow. Don't make it worse. So because the black swan is going... Yes? Okay. Black swan basically is a once-in-a-lifetime event that you absolutely cannot plan against, but it's just going to show up. The financial crisis of 2008 was a black swan. Nicholas Taleb's premise effectively is, without going into too much detail, effectively is the more risk you take out of a system, the more you shove the risk into the tail of whatever you're doing. And when that tail hits you, it's going to be a doozy. which is an entire other discussion about the financial crisis and so on and so forth, but that's the kind of thing you're talking about here. So what we had effectively done was build exactly that kind of a system, where we had set ourselves up so that when the black swan hit, it was a complete doozy. The good news was we're back up in about 8 hours. The bad news is it took us 8 hours to come up. The really entertaining news about that, to digress, you know how we eventually ended up coming back up? Oh, we did a whole bunch of other stuff along those lines, but the key touch there was Greg, one of the sysadmins, was sitting at the colo and he was doing active queue management by pulling our uplinks in and out of the socket, going 2 seconds, 2 seconds, 2 seconds, and he was throttling traffic that way. It worked. It was amazing, but yeah.
In this scenario, what was the black swan? Was it a single server going down or something else? I'm not sure what you did.
Okay, in this particular situation, the deal was we had this very weird congruence of calls coming from a bunch of different places and high. It was the peak. It was between 10 a.m. and noon, East Coast time, which is when most of the people in the world are online at the same time. And at about the same time, the people in Tokyo were just going off and the voicemails were starting to spike to them. I've got like this huge document which I had to do for our board, which was, this is why we're down for 8 hours and this is why we lost $N million, and I'm sorry, but you can't fire me. But, exactly, yes. So yeah, it was one of these things where if you happen to hit everything at just right and we rolled.
But like a resonant frequency?
It actually was one of those things. Yes, cascade failures. So, how do you prevent yourself from shooting yourself in the foot? It's all about fault tolerance. It begins with fault tolerance, it ends with fault tolerance. You have to build your system to be fault tolerant. It's a little known thing, but there's actually a formal definition of fault tolerance. It just isn't, hey, fault tolerance. Make sure that you're reliable. There are 6 very specific things that anything needs to possess for it to be fault tolerant. If you break it down, it comes out to the following. Thing number 1, concurrency. You need to be able to do more than one thing at the same time. Why so? If you can only do one thing at a time and that one thing hangs, you're dead. So you gotta have at least one other thing that can say, yo, this thing's hung, kill it. So concurrency. Fault detection. You gotta know something's busted. If you don't know it's busted, you can't fix it. You gotta know what's busted. When it gets busted, you gotta contain the effects. Ooh, wow. That person over there is coughing. It's either Ebola or something stuck in their throat. You identified a fault. You detected a fault. They're coughing. You're trying to identify what it is, Ebola or something stuck in their throat. If it's something stuck in their throat, you don't care. If it's Ebola, you want to bubble, whatever. Exactly, quarantine, air encapsulation. You got to be able to fix the problem. Code upgrades. When we're talking about fixing the problem, we're not necessarily talking about, shut everything down and bring everything back up again. We're talking about don't in place, in situ fixing of the problem. Remember, you're running multiple things at the same time. You want the things to be able to continue working to the extent that they can while you're fixing it. And the last one, which is a bit of a tricky one, which again deserves its own talk, I won't get into it too much, stable storage. And the point behind this is you need to be able to return to a last known good state. You need to be able to say, oh, hey, yeah, over here everything was good. I can now go back and reassess the situation and figure out what I want to be able to do. That kind of an environment. So these are the big 6. Concurrency, fault detection, fault identification, error encapsulation, code upgrades, and stable storage. Formally defined. If your system, if your language, if your processes have these 6 things, and you're doing them properly, you will have a fault tolerant system. You can pretend you have a fault tolerant system if you have some of these, but there is a failure mode somewhere out there that's going to bite you in the butt. Which takes us to Erlang, which is kind of the point behind this. The secret. This is where the rubber hits the road. Years and years and years ago, Joe Armstrong captured lightning in a bottle. It's an entire other story, but he basically figured out that these 6 things formally can be implemented in a language in an interconnecting, interlocked way, so that you would have a language that can be a language and an environment that can be used to build fault-tolerant systems. And let's kind of take these one at a time. Why these are relevant in a language. So start with concurrency. You got to be able to do things at the same time. Yes, absolutely, it's true. You can do things concurrently in like an infinity of languages. Hell, you can do it in assembler. I mean, you can write it in anything. The difference is, formally within Erlang, it's kind of baked into the genes of Erlang, for lack of a better word. To give you a bit of context, kind of take a look at the typical way you write concurrent code in most languages. What you do is, there's a bunch of concurrency horror that you deal with. Mutexes and semaphores and shared memory and inter-process communication and pick your poison. It's doable. Hell, I mean, Google writing concurrent applications in Java. You'll get like 8,000 hits. Or, there's everything else that does these things. I'm not saying it's not doable anywhere else. The difference is, it's basically the equivalent of giving somebody enough rope to hang themselves versus giving them enough rope and making sure that they don't hang themselves. If you're writing it in Java, it is the easiest thing in the world for you to end up shooting yourself in the foot. It is. You miss one little tiny thing and boom, you're dead. In Erlang, you really have to fight to get to the point where you will have shared memory somewhere. You can do it. It's possible. You have to mess around with the process registry. People do it too. But people do. When the universe comes to an end, it's because somebody's going to look at the big red button somewhere that says do not push, and they pushed it. It's going to happen. So effectively what you end up in Erlang is you lose this part. You're basically writing the system that you want to write without worrying about the details of mutexes and semaphores and IPC and all that stuff. That said, that's a lie. That's actually not the way the system works. What you actually have is more like this. What people tend to forget is there's stuff that you're trying to build. There's a bunch of deep problems associated with the stuff you're trying to build. And then there's all the crap associated with mutexes and semaphores. Deep problems. Paxos, Raft, whatever. You're trying to do some kind of distributed leader election algorithm. That's a deep problem. It's hard. I mean, Raft just came out recently, and it's like the new thing or whatever. That's not going away. You still have to solve that problem. But you don't have to worry about this stuff. And that Erlang gives you for sure. Fault detection.
So,
Yes?
Is this like abstraction over semaphores and all that stuff?
Actually, no. Essentially what ends up happening is in Erlang, at a very basic level, you have the lowest thing that exists is a process. A process is right now it's about a 500 byte entity, which is kind of the equivalent of an old school Allen Kay object. So think of it as a thing it's an actor. It's an actor. Now, effectively what it does is it contains its data, it contains its methods. The data is immutable, it's functional. The data is immutable, methods are invoked by messages, and the only way to get the process to do something is to send it a message. So effectively what happens is, when you look at a running Erlang system, you've got like millions of processes running around, and they're all sending messages to each other. It's kind of like a crowded room where everybody's talking to everybody else. There yes, there is complexity involved in this because you have to think concurrently. You can't think, I'm going to do this, then I'm going to do this, then I'm going to do this. It's like they're all running at the same time and they're all talking to each other. But,
You want to micromanage the processes.
bingo, and that is the
Yeah,
point.
There is, of course, semaphores and vents at the bottom, but they're
Right.
really at the bottom. Like there are
Very-
units. I mean,
Yes, exactly.
Just clarification, these are airlink processes, not like Unix processes.
That is precisely the case. They've got nothing to do with threads. They've got nothing to do with whatever. The term process is a poor term. In fact, I was just discussing this earlier, this goes very deep into the guts of the way the Erlang virtual machine works. If you look at the scheduler for the Beam, which is the virtual machine for Erlang, look at the way the scheduler works. Every single thing that runs, every single atomic command that runs in Erlang is parameterized. It's got a certain number of things called reductions. Just call them wazoos. It doesn't really matter. It's got a certain number of wazoos that each one must run or takes when it runs. What the scheduler does is it says, I'm going to give each process 4 wazoos before I move on to the next one. So effectively, it is physically impossible for a process to hog a CPU. You can't. It is a near real-time system. It's unlike in Go or C or Java or anything else where an ill-behaved process can basically go, you're toast. Here you can't, because after a certain number of reductions, the scheduler's going to go, you're out of here, and go to the next one. So, fault detection. Here's a simple piece of Erlang code. Effectively, that's a method that gets called, and all you're doing is you're saying, I want to feed the cat, and I give the cat some food. And the thing is, depending on what the food is that you give the cat, you get different responses. Only one of the responses is a good response. The rest of the responses pretty much suck from your perspective. Now, note what happens when I give the cat oatmeal. This is, by the way, a match. And OK status is not going to match error unhappy. It's just going to barf all over the place when this thing happens. What happens is, to begin with, this is the fault detection part. It is going to barf. It's going to throw an exception the moment that happens. Cool, I detected the fault. That's it. Simple. Pattern matching.
Is this a function call or function definition? Is this a function call or function
It's a function call.
The first 2 lines are
Or a function definition?
Yeah, this is a function call. This is also a function call. They're all function calls.
Okay.
It's functions all the way down to the bottom. The difference being that, actually, to take this a step
A
back.
little prologue is on
It's
Yeah.
Prolog at the heart. I mean, it basically is Prolog, and Robert Birding, when he started writing this, was the Prolog guy, so he said, cool, I'm going to write this Prolog style, and then it kind of evolved. By the way, one of the very common complaints you get about Erlang is, ooh, the syntax sucks. And it does kind of suck, but in my opinion, it's a good thing that it sucks, because when you look at the syntax, it really doesn't resemble things that you see commonly. And that makes you not think of this in terms that you would think of other things.
You don't have to make this case to a Lisp audience.
Okay, then that's a fair point. I take it all back. Absolutely fair. Yeah. True. So, fault identification. The next one. So we saw the code earlier. A huge problem when something barfs, something explodes. What's the first thing that you end up with? You get a stack trace. Stack traces are the worst thing in the world. Except in Erlang, where they're the best things in the world. Basically, what you pray for is a stack trace.
They're pretty cool in this.
They're wonderful. Yes. The usefulness in a immutable variable world is, in a concurrent immutable variable world, is something which is a joy to behold. I mean, that's basically the best way to describe this. To do the really dumb and stupid example, immutable variables, everybody knows what they are, but that makes no sense in an immutable world. You already set it to 1, how can you possibly set it to 2? And that is like a really ridiculous statement. It's like, why would you ever do something dumb like that?
The bagger should be smacked.
Yeah, seriously, yes. we spend our lives unlearning everything we learned in high school. Or nowadays, it's even worse, everything I learned in high school. Nowadays, people learn to do two completely separate things at the same time in high school. Yes, this is algebra, and yes, this is programming, and oh yeah, they do exactly opposite things. It's like, yeah, whatever. So, back to our cat, our unhappy cat. If you fed the cat oatmeal, you'd immediately get a stack trace. And the stack trace would say, OK status does not match error unhappy. So you'd go, wow, error unhappy, that only happens when there's oatmeal. And you'd see in the stack trace, it says, OK status does not match error unhappy, it barfed out here, and go back up and say that had barfed at line 20, when food came in as oatmeal, and then if you follow, the trace would go all the way back up and say some other process over here sent a message to this thing saying, feed the cat oatmeal, and right at the beginning of the day, way over here, there's something that said, Mahesh was dumb. But that point is something that you get in one single shot in your stack trace. The single biggest enemy of this stuff, of being able to use stack traces to figure out what's wrong with the system, is when you're setting your system up, you have this remarkable tendency. Nobody ever is able to set the debug level on their error messages correctly. It's physically impossible. Whatever you pick is going to be the wrong choice. So invariably what ends up happening is you get something that just says, oh, by the way, this crashed, and you don't know why it crashed. So then you go back in and then you change the debug level, and the next time it crashes, it tells you why it crashed, and life is good. But anyhow. Yes?
I'm sorry, this is just really out of curiosity, but can you imagine somewhere in the background you're using unification to do the matching?
Sorry, say again?
You're using unification to do the matching?
Actually, no.
Okay, that's not actually my question. But
Right, no. It's, what's that?
Okay, but the actual question is, okay, so OK and status don't match error and happy.
Correct.
But there's a partial match of unhappy and status.
No, there isn't.
No?
No.
Status is a variable.
It is, status is a variable, but essentially what happens is it's a left to right match.
Oh, I see, gotcha.
It's a very simple left to right match.
So if it was the other way around, the status would get bound, and then the match would fail.
It would actually not get bound because it,
If it fails, it
Oh, fails to no line.
bingo.
I was wondering if you got partial bindings on
Yeah, and the answer is no, it doesn't. And the reason it doesn't is the whole minimizing side effects kind of situation. What you want to do is have everything happen either all or none. So at every single line that you go through, when you actually break this out, this stuff gets compiled into something called core Erlang, which is the native language of the Beam. And to wind this way back, when you right, so it's effectively the way the system works is you write your application in Erlang. Then when you run the compiler on the thing, it generates something called an abstract syntax tree, which is just a bunch of, well, you guys know what that is. So
We program it.
I know, yeah, that's why I have to keep like unwinding my talk on this one. Then it takes that abstract syntax tree and rewrites it as something called core Erlang, which is not Erlang. It is Erlang-like, but it is essentially what the Beam actually runs. That absolutely positively must be correct. We've got, I think today there are exactly 3 people that understand how the Beam actually works. There are 4, but Patrick just joined Google about a week ago. And
Forget that.
no, seriously, Patrick is, yeah, he's gone. He's lost to us at this point. But actually he went there because they want to move some of the Go scheduling mechanisms to be more reliably concurrent, and I have no idea how they're going to do that, but more power to them. So, continuing. Error encapsulation. This one's a wee bit trickier, but this is, it's kind of like a fundamental Erlang concept. You've heard of, if you've read anything about Erlang or heard about it, you've heard of the whole let it crash thing. The idea behind let it crash is when, fail fast, fail quickly, fail rapidly, fail fast. When a process does something wrong, when you see that, OK status equals error unhappy. Typically, what happens in this kind of environment is you actually just kill the process. You write your system so that the process itself says, go feed the cat, poof, process dead. When you write your system from the ground up to be like this, it actually helps. It helps at a bunch of different levels. Probably one of the biggest ones, which you tend to not think about, is garbage collection. When a process crashes, you have instant, immediate garbage collection of every damn thing the process was using. By writing your system so that it's nothing but a bajillion processes, each of which spins up, does a little bit of something, and then vanishes or crashes, you're getting constant, permanent garbage collection. You don't need to worry about real garbage collection. You don't need to worry about stop the world stuff. You don't need to worry about memory allocation and all that good jazz. By the way, everything I said is a lie. Once you get to the point where you're doing really deep stuff, you will end up worrying about garbage collection and stuff, but that's a good problem to have at that point. I mean, you're way deep into the whole thing. Which kind of leads into the Beam that I was just mentioning earlier. The Beam is the core virtual machine that Erlang runs on. It is insanely stable. It is rock solid. It is solid to the point that the heat death of the universe will come before something bad happens to it. By the way, I'm actually being somewhat serious about this. Core Erlang that I mentioned is a very small set of commands. Virtually all of it, and I believe there are exactly 3, maybe 4 places now, but virtually all of it is lock-free. I mean, to your point, when it gets down there, there are 3, maybe 4 places inside where there are still a couple of locking algorithms. Everybody knows where they are. As you can imagine, it is some frightfully complicated work necessary to get that removed from the system, but that is going to happen one of these days. It is provably reliable, well, almost provably reliable, because not quite going to that extent. But part of the context behind this, of course, is that if you look around, you'll see all sorts of fun things about, well, you know, our environment is good because of this, use the JVM because of that, stupid point. How come you don't run on the JVM? Well, yeah, there's something called Erlang that runs on the JVM, but do you want to run on the JVM? I mean, I probably don't need to go into detail on that point. Code upgrade.
And does this mean that there really is no process level garbage collector?
There actually is. It's a 2-stage garbage collector. Effectively, what happens is, okay, so without going too far into this thing, when you look at the garbage collection mechanism, the way it works is if objects are referenced more than once, they end up getting pushed into a long-term storage.
Yeah.
Otherwise, poof. So it's a standard 2-stage garbage collection mechanism. It's very simple, but it is very simple. When I say very simple, I explicitly mean mean in the sense of it has very few bells and whistles. But there's a point behind this. You make it simple and understandable so that when you get to the point where you have to deal with garbage collection, you can go, that's it. There's not much else going on there.
There are 2 strategies. One is to make something so simple it's obviously correct. The other is to make it so complicated.
Right, yeah. Hello, JVM. But
Yeah.
yes, that kind of a thing.
That it is not, that you cannot show it as wrong.
Oh, that is harsh. Good one. Yeah, we frequently run into garbage collection. The second last major garbage collection bug was one that I found. And it turned out to be a feature, not a bug. It's basically it's one of these things where, to kind of explain this, if you have a process that gets a message and sends a message on, and there is a reference to a binary that comes in on the message here and goes out there, just the fact that this process in the middle saw the message and passed it on is sufficient to keep that reference lying around till this process dies. It's reference counted. It's simple. It's obvious. It's like, well, you want it to be reference counted because maybe I'm doing something with a binary. You never know. But these are the type of things that...
In other words, when you you send a packet, you don't free it.
Exactly.
That sounds like a mistake.
Except it's not, because the way it tends to work is most of the time your process doesn't last long enough for it to give a damn about these things. Most of the contents of the messages tend to be things that are small enough that they can just be chucked. This I didn't get into too much. I won't get into too much detail about this because it's one of these, and the binary needs to be of this particular type, and you need to have done these things to the binary, and so on and so forth. And eventually, when you realize you're getting these out-of-memory errors, you track it down, and then, strange enough, Robert Birding was the one who incidentally clued me in, and then I read the source code and I found out what is going on. But, which also is a good point in that the source code is, for everything, including the beam, is readable, and you can figure out what's going on, which is great. So, code upgrade. Code upgrade is actually a ludicrously trivial thing in Erlang. Yes?
What's the beam written in?
Erlang.
Yes.
Core Erlang. It's kind of your standard thingy.
Isn't there a
There-
major part of Erlang that's C?
C++. C and C++. They're replacing chunks of it, reasonable chunks of it, for performance, basically. So effectively, any place where you want just like bare metal performance, you write it in C or C++ appropriately. I forget what variant of C++, but it's some variant. But so effectively, a bunch of code here. The only really relevant point here is, ignore this for just a moment. The way Erlang works is anything that is referencing a piece of code when it's running will continue to use that piece of code till it either dies or goes out of scope. If you want to upgrade the second piece of code, you run this particular routine on the piece of code that's out here. The moment this thing goes out of scope, the next time it comes back in, it's going to find a new piece of code. So effectively what that means is when you change the functionality, when you change the functioning of anything, everything continues to work exactly the way it was working till they're done with whatever they're doing. The next time they want to use it, they get the new functionality. It's very predictable. It's not monkey patching. You're not doing, entertaining things, trying to figure out what's going on. It's a very specific, very clear-cut, very well-defined way of accessing current and future functionality. This particular piece of code, effectively what this is saying is your old code had some state associated with it. What you're just telling that program is do some bunch of stuff with the old state and return whatever you want the new state to be. Context, supposing you got a routine that takes 3 parameters. You want to replace it with something that takes 4. Classic example. In pretty much every other environment, if you just load the thing, do a hot code load of some kind, seriously entertaining effects as messages come in or method calls come in with 4 parameters instead of 3, and it's like, what are you trying to do? Or you write something on the stack that you didn't expect, or things. Here what you're basically doing is your old thing had 3 parameters, the new thing's got 4 parameters. Anything that's coming in with 3 parameters and is still in scope is just going to keep working perfectly. When you switch to the version that's got 4, if you wanted to maintain some state in there, as in, yeah, you know what, just make sure that the value of foo is 13 when you go across. It'll do that. There's one additional step that you can also do. You can also pass in a version number. What that essentially means is only do this if you're currently running on version 13. If you're already upgraded, don't do anything. So effectively, this is, by the way, just one of the mechanisms that's available for code upgrades. But the point that I'm trying to get at here is there's a very formal clear, clean-cut mechanism by which you can patch running systems without killing anything.
So
With-
the granularity of this is the process.
At the process
I
level,
mean, if you replace your caller, for instance,
right,
presumably nothing happens to your own stack.
that is correct.
Okay.
Absolutely. But it,
So when does the new caller become effective? When he gets control again? When does that happen? When his caller gets control or what?
right.
If foo calls bar calls Baz and Baz replaces bar,
right.
when does the new bar come into effect? Is that when?
The very next time it is accessed by food.
Okay.
Yeah.
All right.
That's the way
So-
it works in Commons.
Exactly. Yes.
You can go into your whiteboard, recompile as much code as you want, but if it's running, it's not actually.
It's never gonna get
until it
touched.
gets re-entered.
So that
Bingo.
means that if the virtual machine has inlined it, it has to be quite clever about the optimizing.
Bingo. And the way it does that is by being very clever.
Same as the JVM action.
Exactly, yeah. The essentially what ends up happening with a lot of these things is you end up writing. So I'm talking about Erlang. There's this entire other level that's called OTP, which is essentially a bunch of abstractions that are put on top of Erlang that allow you to do more complex things. There's Gen Server, which is a mechanism by which you can write client-server applications. Horrible terminology. You can, when I say client-server, what I'm referring to is you got a thing that is a server that is serving some functionality, and you got a thing that's a client that can access the functionality on the server. They're basically two processes that are talking to each other. You got GenFSM, which is finite state machines that you can implement. You have GenEvent, which is event handling mechanisms you can implement. GenTCP, GenUDP, TCP handlers, UDP handlers. You get the point. UTP handlers for BitTorrent stuff. There are a couple more that I can't think of right now, but yes, there's a bunch of these. These mechanisms are actually used to upgrade higher level entities. So typically what happens is you package up your processes into servers, these higher level abstractions that I mentioned. You package up these higher level abstractions into what we call releases. A release is basically, think of it as a tarball or a tarball. You just dump it in the server and say, okay, so this is what you want to run. What this does is it allows you to migrate from between release versions across all the different little tiny pieces in the release version. So your release 2.1.3, you want to move it to 2.1.4, and you're updating the functionality of about 85 different things. You can orchestrate all of that through this. So you can say, upgrade these three first, and then upgrade this, then do something else here, and then do something else here, and it'll cascade the upgrades all through the system. So predictability, always a good thing.
In this example, what stuff? Does Erlang support higher order functions? Is that code?
It is any Erlang. It could either be just parameters, it could be functions, it could be, and yes, Erlang supports higher order functions. You can have functions that reference functions that reference functions, all the way through, down the food chain. Typically what you end up with in here is exactly that. You pass as a handler, you pass handlers to, we call them MFAs, modules, functions, attributes. So you basically say in this module, these functions, these attributes, go do something with it. And that takes care of it. Which is kind of your classic code upgrade thing. You've seen the video for this one, right? It's a big, huge thing. It's like they change the tires in real time. But that's exactly what it's like.
Yes, but the car is actually moving while they're doing that.
Yes, which is unreal. It's kind of freaky.
It's actually balanced.
If I were going to do that, I'd have at least 6.
Yes.
I'm just curious about managing your code base when you do an operation like that. Because you've got, so the release tarball is the properly updated function that'll go from 3 to 4 parameters.
Correct.
For example. Then you've got these snippets out there that you're pushing this rule or something. Do you want to track those? I mean, does that get to be a problem in terms of, I go from release A to B, in between I've done these snippets of upgrades that
Right.
I'm
So,
not tracking or saving.
bit of a trick question. This actually goes back to the encapsulation concept that I brought up earlier. When I said error encapsulation, what you actually end up doing is, since in Erlang, everything's a process, everything's disconnected, you tend to write systems so that their functionality is very tightly encapsulated with strong APIs, message boundaries between them. So yes, you could seriously screw yourself up if you wanted to by randomly sending things out and not knowing what's going on where. But the habit tends to be releasing often, releasing frequently, releasing twice a day, 3 times a day, whatever. So the number of things that tend to go out in a release tend to be very small. So no, you would not actually send out 150 different changes of the 3 to 4 parameters style. What you usually would do is 150 different changes, which are all bug fixes. And with continuous integration and common tests and unit tests and quick check and things like that. Quick check, by the way, anybody know what quick check is? 2. Okay. Functional property-based testing. Anybody? 2. Okay. Basically, the way it works is in functional programming languages, one of the things that you can do is you can basically say, you can define the types of the parameters that get passed into the functions and the types of the parameters that need to come out the other side. In fact, you do define them as part of your application. So, for example, here I would say, where'd this go? I would say this one, the type of the parameter that comes here is an atom, and the output is a tuple, which is the first word is first word is okay, and the second word is another atom, which is one of these 4 things. That's just actually only this one. Anything else is a failure, and it's going to throw an exception. So the input is any old atom. The output must be okay purring. Anything else is a failure. So effectively, what you can do is, if I see that as a specification, I can then have an automated system. Quick check in Haskell, it's also called quick check in Erlang. What I can do is I can build an automated system that just says, okay, I'm just going to throw a whole bunch of random things of type atom in on this end and see what I get at the other end. If I ever get something out that's not purring or an exception, you, Mahesh, have a problem. Yes?
Is dialyzer comparable to?
Dialyzer is what you need to use to do type checking. If the program dialyzes, then you can run proper or quick check against it to be able to do that.
Oh, so it's
Exactly.
not, it's only
Yeah.
part of the process to do quick check.
Right.
It's not-
Yeah, the thing is, Erlang does not have is not strongly typed. Erlang can't be strongly typed. But because of that, the workaround is dialyzer. What that allows you to do is to build a typing system that kind of works on top of it.
Does that mean it's not statically typed?
It's not statically typed, it's dynamically typed. So,
The point about dialyzer is that it, rather than only accepting programs which are provably correct, it rejects only programs that are provably incorrect.
bingo.
It's a very fundamental difference.
Costas Sagonis, who is the prime mover of dialyzer, is famous for saying dialyzer is never wrong. And which, as you can well imagine, has been corrected to now say Costas is never wrong. But and if you say that to him, he'll go, that is correct. And he's a good guy.
You can dialyze yourself improve.
Yes. They actually ran dialyzer on dialyzer, and it worked. I mean, it was great. Couple intangibles, relevant things. One, and this is compared to what? Java, C, C++, standard stuff. Say again?
Yeah.
Yes, well, actually, technically accurate. I was mentioning earlier, I've started dabbling with APL, in which any application that's more than like 32 glyphs is a huge application. You're like, okay, not fair. But bit of story behind this. The phone system that I described, the whole thing was written in Java. We rewrote the entire phone system ground up in Erlang. First pass code base went down by 4x. Second rewrite, once we rewrote it properly as compared to we're learning Erlang and we're writing this stuff, about 3 years later we rewrote it again. It was 9.3x, 10x is an exaggeration. It's 9.3x smaller than the original version. Yes? Because I have a pretty basic rule that says the third time you touch anything, you have to refactor it. And we had refactored enough things that it got to the point that said refactor the whole damn thing. It's
I was actually being asked
Mhm.
the story of the big meltdown where everything failed. Was that when it was in Java?
It is in Java. Yes. It would have happened in Erlang too. It was not
That's
a.
what I wasn't
yeah.
sure whether there was.
No, no correlation there.
Yeah.
It would have happened. Would not have happened the same way, but it would have happened. The thing about this though is
The feedback loop was part of it was inside a human being, and there wasn't any fixing that.
you just can't.
Yeah, but not by, at any rate, not by rewriting a different
Right.
program.
The
Now,
thing.
if the phone gives a fatal shock when WPOL doesn't go through,
Then
then you'd be okay. Die fast.
Actually, it's pretty funny. It's actually pretty funny because amongst the things that we did to fix that, one was we turned off voicemail transcriptions. We just turned off any recording, anything that we had to do, and most importantly, we made all phone calls free. Seriously, I mean, that is the single biggest thing. We just turned off all of our metering and our logging and our tracking and everything. We said, you can't make international phone calls. Other than that, just go to it. It's shocking. Something like 99.9% of the load on the system was just all the crap associated with being a phone company. The phone calls are like nothing.
Wait. I think there's room for something that's very much like the telephone system, but you don't meter it closely. You might have a bunch of networks, and they're interconnected, and it's called. Sorry.
Yeah, so. Here's something that's not funny.
Yeah.
In 1994, I was there for this whole thing. MCI, this was a long time ago. In 1994, MCI sat around Bert Roberts and Tim McDonald, and I was a fly on the wall. Two of the presidents at MCI were sitting on a table, and they're throwing stuff against the wall like, what can we do to gain market share against AT&T and Sprint and blah, blah, blah. And what they came up with was, you know what? $20 all you can eat. That's it. We won't even give them a bill. You just pay us $20 a month and you got your phone. That's it. And they went through, and it turned out back then the regulatory environment was amenable to doing this. You didn't have to give people bills. And when I say no bills, I mean no bills. It's like $20, your phone number works. That is it. They went through the entire process, and when push came to shove, they didn't do it. But what they basically figured out, one of the main reasons they didn't do it was it turned out they'd have to like eliminate about 80% of the company. Because
This brings the power of competition to make things more efficient.
I know, think how different the world would be though today if they'd done that. I mean, this is,
Well, that is the world we're in now, pretty much.
no, 1994, 20 years later, 20 years. Yeah,
That's about right. It takes about 20 years to get things out of the lab.
I know, and it's sad. So, brief context about
The older
code sites.
generation has to die or retire.
Us peoples, basically. We're the ones responsible. All of us, basically. So just to wing through some of these things, the point behind reducing code, really the point behind reducing code is less code you have to write, the faster you can write the stuff, unless it's APL, in which case it's a separate story. For those of you that don't know APL, you write in glyphs, and it really is a truism. It's a 10,000 hour rule. You have no idea what you're doing for the first 10,000 hours. Smaller code is easier to reason about. Absolutely true. Less stuff there is, the easier to figure out. And this is the worst part of the thing, fewer bugs. So it turns out there's a study, a big, huge longitudinal study across everything that they did, where it basically turned out that the number of bugs, quotes are on bugs, don't even ask me what it means, the number of bugs per 100 lines of code is approximately 1.4. It turns out it doesn't matter what the language is, doesn't matter what you're doing, there are bugs in it. Less code you have, less bugs you have. Simple. I mean, it's like a very basic thing. It doesn't even matter. And my favorite, speedy refactoring. Each time you rewrite it, you have to rewrite less of it. And that's a good thing. Things that you don't realize are useful till you realize they're useful. Erlang processes are location invariant. A process on my node is exactly the same as a process on some other nodes. On a totally different node, you don't care about where things are running. It just runs as a mesh across all the nodes that you care about, which is concurrent systems, right? Passing messages, you don't care about where the source and the destination are. The thing about this, though, is it makes debugging running systems awesomely trivial. If there is something weird going on one of the nodes, you just connect to the node. You connect your REPL to the node. You're there. You're on the thing. You're doing live debugging. You're just taking a look at stuff. Attach a tracer, there is such a thing, to a particular module, to a message from module, and you can see where a particular parameter in a message from a function in a module, where it passed through. This is the binary thing that you're mentioning earlier. You can see where it went in its life cycle before it got garbage collected. And by the way, I don't mean in some deep, dark stack trace. You get nice, pretty little printouts that show you what's going on. It's most of the time you figure out what's going on like that. Steep learning curve, incredibly useful to use. The reductions that I mentioned, predictability. Erlang is a near real-time system. You know what is going to happen. You will not have situations in which something runs for a while and then suddenly hangs. Okay, that's a lie. You can make it do that. Not easily and not early on. Eventually you'll get to the point where it will happen and you'll be dealing with stuff. Performance. It's actually ludicrously fast as long as you're not doing things like FFTs or something. It's crazy fast. Crazy, crazy fast. To just kind of
floating point performance is always the
right, and you know what? Write in R or write in C or write in something else if you're going to do stuff like that.
Because everybody has to, all the floating point numbers have to be allocated on a heap, and it just chews you up.
And Erlang is interpreted. At the end of the day, it's an interpreted language, interpreted environment. You cannot get around that. There's nothing you can do about that.
You can make that fast. I mean, you could have a very nice JIT that made that go away, but
Why is there nothing you can do about that?
Say again?
Why is there nothing you can do about that?
Part of it is
It's gotta be
because
possible to write Erlang compiler.
very hard.
You've heard-
Very, very hard because of the core Erlang and the Beam thing that's going on.
Oh,
You
okay.
know,
I'm sorry.
well, mostly because
Because you
your code.
compile Erlang code and you end up with a beam file, so.
Yeah, but that's not really compiling. That's byte compiling.
it's byte compiling.
Okay.
That's the point.
The
You
point
mean
is,
not
you,
compile it to the native.
yeah, you
Right.
should be able to write a JIT. If there are only
Right.
4 people who understand
There-
VM, then there are probably only 0.4 people who understand
Right.
how to write a JIT for it.
So there is a JIT. It's called HIP, High Performance Erlang.
Okay.
And the problem with HIP is it works incredibly well, except when it doesn't.
Yeah, that's
And-
the problem with all JITs.
Yeah, and that's
When they fail, nobody knows why.
bingo. And it's just hard. I've got about 3 minutes, which I'm going to blast through a couple of things on this one, just to bring home the philosophy point here. The Buddha nature of Erlang. Remember I mentioned it's not just a language, it's the way you build systems, the way you build environments, so on and so forth. If you look at fault-tolerant systems, one of the things is you would hope people learn from their mistakes. By the way, the point isn't that that's a mistake. The point is we were responsible for the Obama campaign's voter. if there were problems at any voting center, there were these phone banks that you're supposed to be able to call and say, hey, they're not accepting me, the lines are too long, stuff like that. We were responsible for this back in 2008. We had this monster capacity that we had set up, barely trickling over. It was perfectly fine. And we had set up our redundancy 7 ways to Sunday. And we started getting calls from the campaign saying, everybody's getting busy signals, what's going on, why are you guys down? And we're like, we're not down, we're fine. Turned out all the calls from Ohio were being routed through like one central office somewhere in Akron or something like that. No, they just, good question. I don't know.
That's which was Ohio.
Yes, it's Ohio. Very good question. I don't have an answer. But the funny thing is, you go through all of this, fast forward 12 years, the Project Orca thing that the Romney campaign set up, big, monster, huge thing, set up in Boston Garden. 2 problems. They didn't check the data capacity out of the garden. They didn't. Turned out they didn't have enough capacity. They found this out on the day of the thing. This was exactly the same as the Akron, Ohio thing. There just wasn't enough capacity. Maybe it was somebody doing it again, but the point was there wasn't enough capacity. The second thing was they also had cascade failures. They had no redundancy. They didn't even know that there was a problem, fault detection. When they found out that stuff wasn't working, they didn't know why it wasn't working, no fault identification. They couldn't encapsulate the problem. It was just like, there's a problem somewhere, we don't know what's going on.
That was Windows.
Right. They couldn't fix it. And it is the most amazing thing. I'm looking at the list of problems, their post-mortem, I'm reading the thing. It's like, I've seen this before. This happened 4 years ago. It's the same document, just different colors. And the thing about all of this is when you build your systems when you build your systems, not your applications, doing this, you can get this through loose coupling. You can get, where did that go? Right, sorry. Just by making sure that the individual components are loosely coupled, you can effectively do the equivalent of processes. You can set your systems up so that a problem in one component does not take down a different component. You can set up back in, sorry. Where'd this go? Right. Another point here. You build your systems so that they're wonderfully done, they're absolutely perfect, they do everything absolutely correct. Odds are it's never going to go in production. It just won't. Something about 90% of all software applications never see the light of day. Oh, by the way, it's not because you did something wrong. It's like, you know what, something else was important, this thing got shelved, company went out of business, that happens too, some other project became more important. The point is, don't bother optimizing. Don't bother trying to make it absolutely correct. Just get it working. Figure out the rest later. If you're not loosely coupled, if you're not encapsulated, if you cannot identify problems right up front, if you can't fix them when they happen, just getting it working is not going to be sufficient because everything is going to be so tightly coupled with everything else that it's just not going to work. The point that I'm trying to get at here is these 6 principles that I mentioned earlier. Where'd it go? These aren't just about Erlang. They're about how you build your systems. They're how you take it a step further. Think of the company you work at right now. How many people do you know of who are hit by a bus safe?
None of them. Not one.
That's
They
bad.
are completely non-redundant in human beings.
That's terrible.
Yeah, it's terrible.
Yeah.
We can't afford it anymore.
And
That is to say, we are a multi-billion-dollar company with a 500-year history. The way you get to be a company with a 500-year history is be really, really cheap.
And I totally hear you.
Yeah.
That's not me. But the point is that happens. And Bob does get hit by a bus, and Jane does get run over by a truck. And the next thing you know, you have a problem. By the way, it's not just about being hit by a bus. It's much, much worse. What's your CFO doing in Brazil? He wasn't supposed to go there. Could happen.
Walking the Appalachian Trail.
Yeah, walking the Appalachian Trail. I'll actually make it much, much, much simpler than this. From a pure, how fault tolerant is your company perspective, your system, whatever it is, Meetup, I should know this, whatever you're doing. Spectacular, wonderful, fault tolerant, dead reliable stuff. Have you ever walked into the finance department of your company? Have you seen what they use? Excel? Seriously? The one thing that has almost taken the world down, it almost takes the world down once every 6 months nowadays. I mean, Reinhardt and Rogoff, because of a stupid 42 lines instead of 43 lines addition mistake on an Excel spreadsheet, took down Europe. Europe is going through hell right now because they couldn't drag the blue line all the way to row 43. They stopped at row 42. This is what the finance department is running on. This is what your company depends on. It doesn't matter how perfect your application is.
Yeah, but there are other redundancies in the system. There are very few companies which, if they fail, would take down the whole thing.
Oh, actually, that's a really depressing statement. As in, there are some companies which, if they fail, will take down the whole planet. But yes, point taken. But the point being, the point that I'm trying to get at here is, we look at the things that we control, it's the software, and we go, yeah, we've got everything under control. And we ignore everything else. And those are just as important.
No. Cable and wireless, yes.
Right. So, to close this out, my company, things that we do, we kind of implement this philosophy at a bunch of different levels. Our application, our huge cloud infrastructure is broken into individual components. There is no component that is so large that it cannot be comprehended by one person. It is then assigned to 2 people. Is it the most efficient way of doing things? Hell no. It's good enough. And it works, and one person gets hit by a bus, I don't care. Functionality is encapsulated. Well, okay, I do care, but I don't want them to be hit by a bus.
Yes, we have an infinite capacity for suffering other people's pains.
Right. But right. But you do that, and you take the efficiency loss in the thing. You make sure that your system is encapsulated. Problems in one area don't affect problems in another area. When there is a problem, you know that you can find it. You know that you can figure out what it is. You know that you can fix it. You know that you can always retreat to a stable place. You can build everything that way. That's Erlang. That's how you do Erlang applications. It's how you build Erlang systems. It's how you do, it's how you build your organization the Erlang way. And I've talked 10 minutes too long, I'm sorry, but got sidetracked.